Hey guys, this video is about tea leaf paradox. Denser liquid or a material is expected to be flung outwards upon stirring. However, under a certain set of circumstances, the opposite happens. In our first experiment, we put a layer of mineral spirits on the top to provide a better demonstration. Before we explain the theory behind this paradox, let's see some videos first. After we shake the bottles, we can observe the different shapes of the water surface. From the left to the right, we gradually increase the thickness of the water layer. Then we capture the peak of the water surface for each of them. As you can see, the effect is less obvious when the water layer is thicker. Then let's go to the theory part.
At first, the jar is in solid body rotation. Here, the Coriolis acceleration 2 omega u0 balances the radial pressure gradient. This pressure gradient is the result of the parabolic surface of the fluid when spun. As the angular velocity is varied, boundary layer friction, most importantly between the bottom of the container and the fluid, is not negligible. This results in some interesting behavior. Viscous effects propagate up within the boundary layer. This results in a decreased circulatory velocity within this layer, which results in a reduced Coriolis acceleration. Thus, the Coriolis acceleration is no longer able to balance the pressure gradient, resulting in flow towards the center. The thickness of the scale where these viscous effects are dominant can be found using kinematic viscosity and omega. Thus, for this experiment, delta should be on the centimeter scale, which seems reasonable. Using two liquids does not cause this effect. This was only done for visualization. By varying the height of the colored water layer, we are sampling the prominence of this center-seeking transport at the height of the water level. As we increase the water height, the height of the water lump decreases until we reach a point where it is no longer observable at all. This is because as we move up from the boundary surface of the container, the viscous effects decrease, therefore the circulatory velocity is not decreased as much, and thus the Coriolis acceleration increases. Once we approximately reach the height of the boundary layer, the viscous effects become negligible and the Coriolis force is again capable of balancing the pressure gradient that previously caused the central lump. This way, we can roughly approximate the boundary layer depth by finding the height of the alcohol-water interface where the surface seems to remain flat. This was shown in the orange container.
For real-world Ackermann transport, a similar effect happens in the ocean. This effect can bring nutrients to the surface along shorelines, which is really important for the ecosystem. The same bulge observed in the colored layer of the container can occur at much large scales as shown in the diagram. These large bulges on the scale of hundreds of kilometers in diameter are called ocean gyres. Most importantly, this effect helps us easily remove sediments during bear breeding. These are the references. Thanks for watching.